First, I'm going to go ahead and record this. And we're going to bring that up. Okay. And so we do the theoretical hydrogens first. The theoretical hydrogens is always what formula? 2n plus 2. You got it. N being the number of carbons, right? So 2 times 7, 14, plus 2, 16. Okay? Now, the next thing you want to go ahead and do is you want to modify that number for these other groups attached, right? And so we'll take that 14 theoretical hydrogens. We already have 8 of them accounted for, right? And so that leaves us with 6 right now. Okay? Nitrogen. Well, nitrogen has 3 bonds, right? So nitrogen always adds a hydrogen in because it always comes along with an extra hydrogen. That was this one here. See that? We have an extra hydrogen it always comes along with. Okay? Okay. Oxygens, well, oxygen doesn't change our numbers because it has 2 bonds. One of those bonds is going to end up being hydrogen if it's not bonded to something else. So, it doesn't change our number at all. Okay, we can ignore the oxygens. We go over to the chlorine. Well, halogens always reduce the number of hydrogens by 1, don't they? Because they're going to have the same number of bonding as hydrogen. Okay, so they make 1 bond, they'll have another spot to put something else. Okay. Okay. And so we had our number, which was originally 14 plus 2, 16, minus 8. That would have been 8. And so then we're going to modify that number, plus 1, 9, and then minus 3, right? That'll leave us with 6. We need to divide that number by 2 to get the IHD. Okay? And so once we divide that number by 2, we get 3. Everybody feel good and understand that okay? Anybody get lost? Okay. All right. And this is the math, by the way, broken into pieces. Okay, so let's go ahead and come up with some strategies for success here for drawing all the constitutional isomers of a given formula. Now, one of the first things you need to figure out the formula, and is sort of like you're used to kind of drawing these things out and having an idea of how they're connected. But when you have a very simple molecular formula, like I gave you here, right? There really isn't a way to do that, especially once we start putting all these different groups we can have, right? We can have double bonds, we can have triple bonds, we can have a ring. There's really no way of you figuring that out here, okay? And so one of the ways you want to do this is you want to first get the IHD number, okay? That's going to at least tell you, if I have an IHD of 1, then I have a ring or a double bond, right? And so now I know that I need to represent a ring or a double bond, right? Something. If I have an IHD of 2, I could have 2 rings, 2 double bonds, some mixture of that. I could also have a triple bond, right? And so that tells me, hey, these are the things I have to watch out for, okay? Okay. The next thing you want to do is you want to draw the possible backbones. Now, when I do this on the homework, there's kind of a convenient thing that you can do, which is you draw out one of the backbones, and then you can highlight that backbone with the highlight tool. And if you're on a Microsoft Windows, you hit Control-C for copy. If you're on an Apple, you hit Command. Yeah, Command. Thank you. Yeah, damn Apple. Command-C. Okay? And then to paste those things, you would then hit Control-V. To paste in Apple, you would hit Command-V. Okay? And that's actually how you can then rapidly take a skeleton structure, make copies of it, and then fill it in otherwise. Okay? And you can do that with just making one, and then make copy, 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 make another, copy, 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 and make all the possible skeleton structures. Okay? So if I had, if I was talking about an IHD of 1, I would need to include a ring as well, right? And so I'd have to make the backbone ring structures as well. Okay? If I don't have an IHD, then I can just make straight chain structures, right? Okay, and I can then remove carbons to put them into branches. Okay. So the next thing you want to do there is leave out any double bonds, triple bonds, or halogen atoms because you want to fill those in later, okay? If you start with them in, you're going to end up having a lot of difficulties later because you're going to have to break them, then make them, right? Break them, then make them. And so it's going to make extra work. Make sure you include rings. Again, that number of rings cannot exceed the IHD. And so if you have an IHD of 1, 2, or 3, any IHD numbers, you're going to probably have ring structures you have to come up with, okay? It's certain. You absolutely will have some sort of isomers that are rings, okay? If you have an IHD of 0, do you need to worry about a ring? No. Can't have a ring, can you? All right. So 3 for each structure generated in step 2, you're going to add double or triple bonds to achieve your total IHD calculation. So you'll add double bonds to achieve it. If you have 2 IHDs you can take care of, then that would be a triple bond you could add in one of those isomers, right? So for each structure that's generated in step 3, you would then add your halogen atoms at various locations to generate as many unique connectivities as possible. Now, one of the things I'm going to add to this is when you're doing these, try to keep everything the exact same shape, okay? And try to keep those double bonds in sets. So like if you add a double bond to that first 1,2 carbon at the beginning of the chain, do that for all the carbons, okay? And then move it over to the next one and do that in a line. And then the next one, do that in a line, okay? So that way you have very easily comparable structures. If you do them as like random mixes and some of them are this way, some of them are that way, yeah, you're just never going to finish because you're going to go there. What am I looking at? Okay. So add the halogen atoms at various locations. Now, when you do this, be systematic about it. And remember, you can double, right? If you have a CH3 portion and you have 3 halogen atoms, you could replace all of those hydrogens, right? Because they take the same number of bonding as a hydrogen, don't they? Okay. Okay, the other thing to remember on this, whenever you do any of these steps, remember your bond. Carbon wants how many bonds? 4. You have 5 bonds to a carbon? No, something's wrong, right? If you have 2 bonds to a carbon, 3 bonds to a carbon, something's wrong, right? Are you going to have typically lone pairs on a carbon? No, that would be a carbanion, and it'd be a very unique case, okay? In fact, the lacking bonds would be a carbocation, in case you're curious. That's a positively charged carbon. Very rare cases, you shouldn't see those, okay? All right, so this right here, we determine the IHD first, right? And what we find out for this one here is this is actually saturated. This has an IHD of 0, in fact, okay? And so do we have to worry about rings or double bonds or any of that? No, we don't have to worry about that. Okay, so number 2, we need to draw out all the possible skeletal structures. We'll make copies of those later, okay? But for now, we just need the possible structures we could end up with for those backbones, okay? And so what are some of the possible backbones we could end up with? Well, we have how many carbons? 4. And so we need combinations of 4, right? There's the straight chain 4. And then the other possibility of 4 is moving one of those methyls right to the center, okay? If we move that methyl to either end, we would just end up with the straight chain, wouldn't we? And see how just doing it like this, so you only have a few things to compare, means that you can tell that really fast. So let's say we had made this and we tried to do a C. And in that C, we went like, okay, I'm going to try to draw this out to really make this as confusing as possible. We went like that in that C. Is that an isomer? It is. Exactly. Yeah. And by looking at it where you just have 3 things to compare and you only have this very limited set of information, it becomes so much easier to see, right? Because all you got to do is just, it's upside down. That's all it is, isn't it? Okay. And so you're exactly right. By moving that bond over, I just made the exact thing. Okay, so once we get those, that's where you're going to start making copies and then filling things in, okay? And you're going to start putting other things in. For this specific problem, because I'm trying to give you something relatively easy to build up on, this has IHD of 0, so we don't have to worry about putting any double or triple bonds in, right? And so we go ahead and make copies, and we add the fluorine atoms. And we start adding those fluorine atoms across, so we get all the different combinations, okay? So for example, this is the copies of A, right? Okay. And then we've added a fluorine atom to the end. We added a fluorine atom to the second position here. And what would happen if we did the third and fourth positions? Yeah, it's the same thing again. And if you do these in nice sets where you have them like contained all in one area, you can see that easily. Okay? If you added it here, you'd go, oh, that's symmetric, isn't it? It's just flipped. Okay? And over here, again, we do the same thing. We add to 1, then we add to the center. And what we end up seeing is if we try to add it over here, for example, well, that would actually just create the exact same thing, wouldn't it? Okay, that would just be E again. If we added it here, that'd also be E again, wouldn't it? Okay. Yeah. And so be very systematic. Break it into small parts. That's kind of how science works, right? You do have to get up to the whole thing eventually, but take it in steps. You don't try to leap up to the third floor here, right? And enter through the window. You go up the stairs. And so even the entry to the science department is science. Okay. Now, the next thing, we're going to add that second fluorine atom to our various sets. So we take our set, we copy all those, we paste them, we bring them down so we have them all contained, right? And now we're going to add the second fluorines to them. Okay? Okay, so we start adding that second fluorine across. So we put, bang, fluorine on the same one, first one. Okay? The second fluorine on the second one. And we try it on the third one. And that is different, isn't it? Cool. Oh my goodness. We have more isomers, don't we? And then we do it on the end. Oh, still different. Okay. Okay. And we tried on the second one, the first one. So see, these are the second set we did before. This one. These are the derivatives of D on that second line. Okay. So we start adding this, and we put it on the first position. And, oh, whoops. Still looks the same, doesn't it? Yeah. So that's not one. We delete that one. Okay. That isomer is just a copy of H. We double up on the second one. That's unique, isn't it? We go to the third one here, 2, 3, also unique again. Okay. We add it to the fourth one, and we go, oh, wait a second. That looks exactly like I. Right there, doesn't it? And so we would delete that one. That one's not right. Okay. Okay. So now we start doing that one where we did the branching. Isopropyl. Right? We again make our copy of our sets, right? So we make a copy of that set. And now we start adding the second fluorines to each of those. And we just go down the line. 1, 2, 3, etc. Okay? And so add it to 1, unique. We add it to 2, unique again, right? Then we add it to 3, and it's still unique, isn't it? Okay, now we add it to this branch. And you see that that's the same as if we added it to that, right? Everybody say okay? Okay. So the next one, we take that other one, and we add it, and we see that, oops, we end up with P again, don't we? Oops, over here. And realistically, if we try to add it in any of these ends, we just end up with the same thing, don't we? Yeah. So that one kind of solves itself pretty quick. Okay. Does anybody have any questions so far? Mhm. Yep. Because we started with one in the center, any of these branches that we add to automatically ends up the exact same. And so it got some disaster, but you can do them individually and go, oh, shoot. Oh, same. Yeah. You'd probably pretty quickly realize, though, because you would have started with this red one only, that when you add the blue one here, it would be the same as adding here or here because they're all the branches, right? Yeah. Any of those could have been your branch. Okay, so this one right here is another example. We take the C3H6O. Our molecule in this case has an IHD of 1. And so one of the things we have to do is we need to make that base structure, right? Skeleton. And don't forget that oxygens can be part of the skeletons, right? So they can be at the end, but they can also be part of the skeleton. They have 2 bonds. Okay. Unlike halogens, that can only make the one, right? Nitrogen, same way. Don't forget to put them into your skeletons. It's one of those places where people start like excluding them and causes issues, right? All right, so this is going to contain a ring here. This is your 1IHD ones that we're doing for that set. And so we have a 3-membered ring with an OH out here. We have a 3-membered ring with the O inside of it. And then you'd have a methyl on it, right? In this case, where the methyl is doesn't matter because we only have 3 things in the ring, right? Over here, we have them all in the ring. And that gives you a 4-membered ring. This is going to be the one with no rings. Okay, and again, we make sure we move our oxygen down through our chain, right? Don't forget, oxygen can't have 3 bonds. So this is a place where people typically get a little bit confused sometimes. And they try to put the oxygen right there, essentially. Okay. Right. So any of the ones that were the straight chains, we actually have to put the double bond on, don't we? Because we have an IHD 1. So we make a copy of all those, bring them down, we put our double bonds in, and in this case right here, well, we can actually move that double bond all the way through the chain. So ding. This one right here, we can only put the 1 double bond here because oxygen can only have 2 bonds, right? And if we put a double bond on this oxygen here, it would be 3 bonds. So can't do that. This one over here, well, if we put the double bond on either of these branches, we end up with the same thing, don't we? Yeah, so that eliminates one of those. You can have the double bond to the oxygen, though, as well. Notice that that's actually 4 bonds to that carbon here. So that will actually complete that one. Okay, and then you just go through. There's no halogens here, so you don't have to worry about that. If you have to express the hydrogens, you do that, but most of these structures, you don't have to worry about the hydrogens because you're just going to do the line angle structure. Okay, so let's talk about some constitutional isomers and biomolecules because I think most of you are more interested in probably biology and biomolecules. Yeah. Can I get an idea of that? Interested more in biochem, biomolecules, that sort of thing? Yeah, it's almost everybody. Not quite. I do have some people that are actually interested in chemistry. Thank you. Okay. Though, if we're being realistic about it, med school in these days and PA school, really it's more chemistry than it is anything else. So, like that's modern medicine for you. Go figure. Yeah. Now, leucine and isoleucine. These are 2 naturally occurring amino acids, of course. Has everybody heard of leucine and isoleucine? Okay, they're 2 of the amino acids. The iso part is literally telling you isomer, isn't it? Okay, that's what that's communicating to you. And so these are going to be constitutional isomers. They have the same molecular formula, but they have different connectivity. And you can actually see that different connectivity right here. These, by the way, are the side chains, those R groups that you would have seen if you ever saw amino acid listed out. So in case you don't know, this right here is the amino portion, right? The amino. Notice the naming is the same for that as organic chemistry. took the organic chemistry naming. Okay? And then this right here is the acid part, right? That's the carboxylic acid. This is referred to as the alpha carbon in case you're ever curious, because it's the one between the two functional groups. Next one over from them. And this right here is the side chain. Typically, this is noted by an R, though it's kind of funny because that's slightly wrong, because you can have a hydrogen here for the side chain, but it's fine. We even abuse that in organic chemistry, so it's fine. Now, this side chain right here, this is the leucine where it has that iso group, by the way. Did everybody catch that? 1, 2, 3, 4. That would normally be called isobutyl. And then the iso one is actually the wrong one. This would be sec, right? Yeah. Those biochemists, sometimes they don't know their naming as well as maybe they should. It's in too many tables now. I can't do anything about it. Anyways, kind of a funny thing. Yeah. So they did kind of misname that one, didn't they? Hopefully this will make you remember it better whenever you're doing this. Now, again, this is going to be the monosaccharides may actually provide many more constitutional isomer examples. So once you start looking at monosaccharides, they're all constitutional isomers of each other. And some are actually enantiomers of each other. So we have a pretty broad spectrum of the different types of isomers when we start looking at different saccharides, carbohydrates, sugars. This is going to be acyl and cyclic sugars. These are going to be the different forms of the sugars. They do have the same formula, but they have different connectivities. So they are actually constitutional isomers. So when you're talking about something like ribose, by the way, this right here would be the straight chain ribose that you typically see in like a book. Okay? Typically has a Fisher projection, which is this up and down structure, okay? With the OHs and hydrogens going across. Right. So when you look at this right here, the majority of ribose is not in the straight chain form. Okay? The vast majority in a physiological environment is in this ring-shaped form. Okay? And this ring-shaped form is actually a constitutional isomer of that ribose. And so it's kind of interesting because you think of ribose usually as the form it's not in most of the time, and the one that it is in most of the time, you kind of just go, it's the same thing, but it's not. It's constitutional isomer, actually. They have slightly different chemical properties and physical properties, and yes. So kind of a funny, amusing, weird thing. Okay? That's the same for glucose, by the way. This right here is the ring form of glucose. 99% of glucose is in this form in your body, in the ring form. Okay? Very little of it is the straight chain form. Though in a physiological environment, to be fair to the biochemistry people, in a physiological environment, the reaction that does this ring closing and opening is very easy to accomplish. Okay? The ingredients you need to do that are just everywhere around this. And so in physiological environments, most of this straight chain form is actually these breaking apart, and then it comes back together and does the ring closing again. Yeah. So these things will interconvert pretty often. Okay, now let's talk about some of the monosaccharide isomers. We have ribose and ribulose. These are isomers that differ by the location of the carbonyl group, actually. And so right here, see, it's on the aldehyde position. Over here, it's on the ketone position. Okay? Anybody know the difference between these namings? Anybody know how sugars are named? No? Okay. Well, I get to introduce you to it. Okay, now, notice you have an aldehyde sugar. So the aldehyde sugars are named with aldo. Aldose is how you actually say that, class. The ketone sugars are named ketoses. Okay, so ketose. Ose meaning saccharide sugar. Okay, meaning carbohydrate. This right here, pent, how many carbons? 5. And so it is an aldopentose because it has an aldehyde and 5 carbons. And we want to say that's a sugar. So ose. Okay. This right here is a ketopentose because it has a ketone and again 5 carbons, right? And again, it's a sugar. Okay. Sugars have the formula CnH2ON. So the same number of waters as carbons if they're monosaccharides, meaning only one of these groups. This glucose right here is going to be aldohexose. It has 6 carbons. Okay. This fructose here, everybody's heard of like high fructose corn syrup. Okay, so really the big difference between fructose and glucose is actually that it's a ketose. It has a ketone instead of an aldehyde. Okay. Do you guys do the Benedict's testing for aldehydes? They do that in biology a lot. It's the blue solution you put in, and it turns like brick red with the precipitate that comes off. Okay. I don't know. What in the world? They're like bringing like, they have, you definitely do it. There's a biology lab where they do that. I know that for a fact. Because they just have like 30 solutions of that in the cabinets over there. And it's like gallons of it every year that gets done. But I don't know what biology lab they do it in. So anyways, so if we're talking about like ribose, by the way, if you remember deoxyribose, that actually has one of these oxygen groups here, removed. Okay. Okay, so let's talk about saturated and unsaturated in fats and oils. So this is some examples of unsaturated fats right here. Okay. This one right here would be a saturated one. This is butyric acid, actually. And this is actually, if you guys ever experienced rancid butter, where it's went bad, it's pretty unusual to actually see, but it's rancid butter. It's if you've ever been to a movie theater and their butter smells like off and wrong, that's rancid butter. That'd be a place you'd usually find it because they don't always clean their instruments and stuff. Or like a really bad diner, like a really terrible diner. Okay. So this right here is stearic acid. Again, this one right here is going to be a saturated fatty acid. Notice it's saturated because it's completely saturated with hydrogens on that chain, right? Okay, and then we have our degrees of unsaturation, don't we? And that's unsaturated fats and oils, unsaturated fatty acids. And that's these ones here. Now note that when you have multiple unsaturation points on your fatty acids, that's typically going to be your essential fatty acids. Those cannot be made by a human. You have to get those in your diet. And so that's what the essential nutrients are. They're things you can't make. Okay? And so you need to ingest these. This is linoleic acid. Saffron oil is one source of it. Linolenic acid. Anybody have any questions there?
Just because there's a double.
Mm-hmm. Yep. It's just because of the double bond. Okay. Being unsaturated, you can have one or more double bonds. Okay. Typically they happen in 1 to 4, and I'm not aware of any single unsaturated fatty acid that's an essential fatty acid, but I'm not a nutritionist, so I don't use this information almost ever, right? But as far as I remember, all the essential fatty acids have 2 or more. One of the things this is used for, have you guys ever heard of like hydrogenated peanut oil? Huh? Yes. Yes. So technically all peanut butter would be hydrogenated. You can make something that tastes a little bit like peanut butter. No, it is not. It doesn't really taste like it either, does it? So the reason you do that is actually, see these melting points here? Okay. So yeah, not just that actually. So what's happening is peanut butter is actually what's called hydrogenated peanut oil. Okay. And so you take peanut oil actually melts at room temperature and is a liquid. Okay. And in fact, if you go to restaurants, you can actually see them brush on peanut oil sometimes to give like peanut flavored bread stuff and fry it. It's actually quite good. So you get most of the flavor of peanut butter if you just brush on peanut oil. It just, you can't coat it with it. It's a very light coating compared, like you're coating with oil. So anyways, what you do with peanut oil actually is a non-saturated fatty acid. And so what you do is you break all these double bonds, go to all single bonds, and that is going to give you a saturated fatty acid. It has a higher melting point, and so it's a solid at room temperature. And then when you put it in your mouth, it starts melting and going to the liquid. And that gives you that like nice, huge flavor explosion. That's peanut butter. Okay? And that's peanut butter. All right. They do that with other things too, like margarine. I don't respect margarine, so I call it hydrogenated oil. Yeah, or fake butter. You got it. It is awful, and it should never be a thing. And they used to force me to eat that crap in the 80s when I was a little small kid, and I will never forgive them for it. Okay? Ever. And that's because it is horrible for your health. The hydrogenation process is an equilibrium. All equilibriums can go backwards, right? So when the hydrogenation process occurs, you break most of these double bonds, but some of them can go backwards. Some of them go back to the cis, but some of them go back to the trans instead. And so that's where the trans fatty acids come from. And in nature, trans fatty acids are extremely rare, very, very, very uncommon. Okay? So anyways, that's that, in case you're wondering. This right here is the effects of the melting points with the fatty acids on the melting points. So when you have a cis double bond, what does that do to your ring? Well, it gives a kink in the chain, right? Sorry, not ring, chain. And so what it does is it actually makes it like this. See that? Where it has a kink in it. Now, when you try to overlap those are not going to overlap as well, are they? Versus these straight chains like this. Okay? This is why that melting point changes and goes down so much. You get a lot less London dispersion forces, right? That also has a huge effect on your cell membranes. So when you're talking about cell membranes, does everybody know that they're mobile? They actually have a lot of liquid properties. Okay, they're not fully solid by any means. And they're supposed to be mobile. They're very much meant to be mobile. They're not mobile, your cell membranes won't function properly, actually. In fact, you have an entire process where you bud off parts of your cell membranes. If they're not mobile, that does not work. What you do is you typically add cholesterol into your cell membranes to change the mobility of it. But if you start getting a bunch of, so cis fatty acids are one of the things you add in there, and it can actually increase that mobility. It can make it so these fatty acids don't stick so well together, right? And increase the mobility. If you get the mobility too low, it's going to be very rigid, and it's also going to be pretty fragile, surprisingly so. If you get the mobility too high, it's just going to pop like a soft balloon, right? And so it's a very careful balance that has a little bit of leeway to it that our bodies do. And this is one of the mechanisms that helps do that. Trans fatty acids do not have a kink in it because they're not on the same side. So they're also zigzag and mostly straight. Okay? Okay. Anybody have any questions? All right. Very good. Hopefully I gave you just enough to be curious and look forward to biochemistry. Hopefully.